Oke, baik. Selamat malam semuanya. Oke, sebentar saya masih set up buat materinya. Mungkin kalau ada yang mau bertanya, boleh open mic. Udah saya kasih akses untuk open mic. Untuk detail Timothy akan dibahas besok. Untuk jadwalnya diubah jadi jam 11. Jam 11 siang hari Sabtu tanggal 2 Juli. Lalu menggunakan Zoom kelas B ya besok. Oke, sebentar. Oke, tanggal 2 Juli demo day ya. Ya, 2 Juli besok akan di-share rekamannya. Jadi ada penjelasan tentang datasetnya dan tidak ada batas waktu selesainya jam berapa. Jadi jam 11 sampai selesai. Jadi masih bisa bertanya di sana tentang datasetnya karena kebetulan kan datasetnya ada 20 ya. 2 Juli itu baru detail demo day-nya aja sih. Detail demo day-nya ngapain gitu. Iya, opsional. Tapi kalau pada udah paham gitu datasetnya, boleh nggak datang sih. Tergantung kalau nanti kan kita kasih ya datasetnya gitu. Kalau memang ada yang mau ditanyain, bisa ditanyain besok jam 11 gitu. Nanti jam 11 malam setelah semuanya atau nanti jam setengah 11-an setelah selesai kelas dan kita kasih record hari ini, kita akan bagikan untuk kelompoknya ya. Ya, aku coba untuk share screen. Oke, hari ini kita masuk ke time series hari ketiga. Agenda hari ini itu kita akan membahas tentang RNN pada time series dan reward time series data. Oke, apakah semuanya udah siap? Hari ini ada banyak lumayan untuk demonya. Oke, kita lanjut. Sedikit recap, kemarin kita udah belajar untuk neural network ya, neural network pada time series gitu. Jadi kita akan lanjut belajar tentang RNN pada time series. Nah, RNN. Jadi RNN atau jaringan syaraf berulang itu adalah model deep learning yang biasanya digunakan untuk menyelesaikan masalah dengan data input berurutan seperti time series. Serangkaian neural network feed forward di mana node tersembunyi terhubung secara seri. RNN memiliki prediksi beberapa seri. Jadi ini ya gambarannya. Jadi kan kita sempat ya kemarin belajar RNN waktu NLP gitu. Nah, kalau yang ini RNN khusus untuk yang time series. Oke, nah ini RNN memiliki lapisan input, lapisan tersembunyi atau hidden layer, sama output layer gitu ya. Jadi ada input, hidden layer, sama output layer. Nah, lapisan input layer itu untuk fungsi aktivasi diterapkan ke lapisan tersembunyi gitu ya. Ini untuk mengambil input, terus fungsi aktivasi diterapkan di lapisan tersembunyi atau hidden layer. Itu yang kayak ReLU gitu ya. Terus ini hasil outputnya. Pada deep neural network itu ada beberapa hidden layer. Jadi ini lapisan hidden layer pertama, yang kedua gitu. Nah, nanti kalau di deep neural network itu lebih banyak hidden layer-nya. Ini yang kayak kemarin kita sempat bahas waktu NLP ya, dia punya bobot dan punya bias gitu, W sama B. Nah, bobot dan bias pada lapisan hidden layer itu berbeda. Kayak kemarin kan sempat ya dibahas waktu kita NLP itu dihitung satu-satu per garisnya buat tahu nilainya gitu. Nah, ini dikarenakan masing-masing lapisan ini berperilaku berbeda atau independen, sehingga tidak dapat digabungkan bersama-sama. Oleh karena itu, kita harus memiliki bobot dan bias yang sama untuk lapisan tersembunyi ini mengikat lapisan tersembunyi lainnya. Jadi kalau hidden layer yang ini mengikat hidden layer yang lain itu harus punya bobot dan bias yang sama gitu. Nah, di RNN itu ada beberapa jenis, ada 4 jenis. Yang pertama itu one-to-one atau yang biasa disebut vanilla neural network. Jadi ini punya single input dan single output. Terus yang selanjutnya one-to-many, dia punya single input tapi punya multiple output. Contohnya nih music generation. Terus ada many-to-one, itu sequence input dan produce single output. Jadi inputnya yang multiple gitu ya, banyak, nanti produce-nya single output. Contohnya itu sentiment classification, prediction of the next word gitu. Terus many to many. Di sini dia akan ngambil multiple input, terus habis itu dia juga akan nge-produce multiple input gitu ya. Ini sequence of input, produce-nya sequence of input. Contohnya ini ya mesin penerjemah translator. Nah, ini contoh arsitekturnya dari one to many to one, one to many, one to one, many to one, many to many. Kalau one to one ini inputnya 1, outputnya 1. One to many inputnya 1, outputnya multiple. Many to one, inputnya multiple, outputnya 1. Terus many to many inputnya multiple, outputnya multiple. Yang tengah ini diibaratkan hidden layer-nya gitu yang hijau. Oke. Nah, di sini ada improvement RNN. Jadi RNN itu punya problem yang biasa disebut sama vanishing gradient descent. Di sini ada yang pernah dengar nggak nih vanishing gradient descent? Salah satu permasalahan yang ada di RNN. Jadi kalau vanishing gradient descent itu kayak namanya ya, jadi dia itu gradien yang hilang gitu ya kayak. Jadi gradien yang hilang dia tuh biasanya ada di RNN, deep learning, yang bagian deep learning gitu ya, deep neural network gitu. Oke, terus habis itu dua improvementnya ada GRU, sama LSTM. Nah, kemarin kita udah sempat bahas GRU sama LSTM ya. Di sini LSTM lebih populer untuk digunakan time series gitu ya. Time series forecasting. Nah, ini contoh beberapa aplikasi kalau kita pakai RNN. Itu ada speech recognition, ada language translation, ada image recognition and its characterization, sama time series forecasting. Oke. Nah, hari ini kita bakalan banyak membahas demonya untuk yang time series forecasting pada RNN, GRU, LSTM gitu ya. Sampai di sini mungkin ada yang mau tanya. Ini beberapa udah dijelasin waktu di kelas NLP kemarin ya. Oke, kalau belum ada yang mau tanya, di sini ada contoh demo untuk yang RNN, LSTM, GRU time series. Nah, tapi di sini juga ada video untuk demo ini. Kalau misal translator Indo-English buat cek hubungan antar kata atau susunan kalimat gimana pakai machine learning. Jadi kita misal inputnya bahasa Indonesia terus outputnya bahasa Inggris gitu ya. Setahu udah ada library yang bisa dipakai buat itu sih. Kalau dulu aku pernah bikin itu pakai Heroku sih, tapi nggak machine learning yang terlalu gitu juga. Ya, sequence to sequence. Dia yang many to many tadi. Biasanya itu kalau mau bikin mesin translator yang cuma sederhana itu udah ada beberapa di GitHub kayak library yang bisa langsung dipakai gitu. Jadi nanti kita kayak tinggal install library yang ada, terus bisa kita pakai buat bikin yang sederhana, translator sederhananya. Itu. Oke, kalau yang ini ada dibahas di video ini. Jadi nanti aku kasih file yang example ini untuk dicoba-coba, terus kita nonton videonya. Gitu. Ini datanya lumayan banyak dan untuk bagian input yang stock time ini nanti ada beberapa data, nggak cuma yang IBM. Kalau yang ini IBM, Tapi kalau untuk yang itu ada beberapa, jadi nanti bisa dicoba-coba yang lain juga. Nih, ada Google, IBM. Kita coba tonton videonya terlebih dahulu. Ini ada Amazon juga, tadi ada Alibaba. Kita tonton videonya terlebih dahulu, lalu nanti aku kasih datasetnya semua untuk bisa diganti-ganti ya. Waktu mau coba ini cuman IBM aja sih yang dijelasin di sini.
Cool. All right. Hi guys, I'm Jakob, and I am hopefully going to tell you how to predict anything in the future. Stock markets, IoT data, weather. Nah. Got your attention, but unfortunately I can't even lay claim to that. But what I am going to show you is how to use LSTMs in a neural network approach to at least get a different understanding and get a maybe slightly better understanding.
Ini subtitlenya bisa di-on-in nih, kalau yang ini gitu. Ya, nanti kalau udah habis ini lumayan bisa buat coba-coba lagi karena banyak banget ini datasetnya, ada yang IBM, ada yang Google, jadi kita coba tonton videonya dulu buat nanti bisa dicoba-coba sendiri gitu.
In terms of using a time series approach rather than the more traditional kind of methods. So I'm just going to give a quick background about myself. As you already mentioned, my main kind of job is a quantitative research developer within a large global investment manager. I'm also an independent consultant for full stack software development and a little bit of machine learning, etc. And I also like to hurl myself out of planes. So rather weird little mix of hobbies, but yeah, that's me. If you've got any questions on that later, I'll be more than happy to answer them. Now, a little bit of background. So this is my first kind of presentation here and meet up with you guys. I'm not an expert in IoT at all. I'm very new and naive to the field, and obviously I haven't met any of you guys either before, so I just want to get a quick show of hands, just to kind of gauge where everyone's at. I'm guessing you all have, but who's heard of neural networks? Pretty much most of you. What about LSTMs? Yeah, a couple. Okay, good.
So assume that people don't know LSTMs.
Yeah.
And assume that people know a little bit about neural networks, but not the detailed theory behind it.
Perfect. That's ideal. That's kind of what I was hoping for. If you were all experts in LSTMs, then this would be a little bit simple, but this is good. So I'm just going to give a kind of overview of, I'm going to give a 60-second overview for those of you who didn't raise their hands on kind of what neural networks are and how they work, kind of vanilla flavors, and then of how LSTMs, which are a kind of extension to normal vanilla neural networks, kind of work. So in 60 seconds, neural networks, essentially they were developed quite a long time ago, kind of 70s, 80s, to essentially mimic the workings of the human brain. They work in the sense that you have stacked layers of neurons, and neurons are essentially just activation functions. The most simple of which is just a sign activation function, and it's combined with a weight that takes the input, multiplies that by a weight, and then if that triggers the activation function, produces an output. And large numbers of neurons stacked in layers can produce quite fun behaviors, as I'm sure you know. It can be used for all sorts of things, and a lot of the kind of deep learning and machine learning approaches used these days to do really crazy and awesome things, using variants of the traditional neural networks that were predicted, that were made back in the 70s and 80s. So the issue with actual normal neural networks, especially on a time series approach, and especially applicable, I'm guessing, to IoT, because a lot of IoT data is kind of sequential time series type data, is that they have a distinct lack of memory. They can't remember. Now, this obviously poses an issue, because if you're looking at sequential data, then having each input or each set of inputs as completely fresh inputs without a history of the past poses a little bit of a challenge. Now, you might think, okay, so the most simple way to introduce memory into these kind of networks would be to just use a feedback loop, right? And that is what people did do in the past, and that's what, where recurrent neural networks, or RNNs, first came about. Essentially, an RNN is the neuron, like a standard vanilla neuron, but the output is also then fed back into the input of the neuron again, giving some term of memory to that neuron, which is all well and good, but RNNs do suffer from one kind of big drawback, and that is something called the vanishing gradient problem. Essentially, these neurons usually have a SAN or a TANH activation function, and if the output, which is between 0 and 1 or -1 and 1, keeps getting multiplied, say even by something very slightly smaller than 1, the output will get very small very quickly. So naturally, that reduces the learning rate of the network itself pretty quickly to an indistinguishable amount, and kind of renders them a little bit useless. Luckily, I think I'm probably going to get the dates wrong on this, but I think around about 2006-07, some guys from Switzerland invented LSTMs. Now, LSTMs stand for long short-term memory neural networks, and they're essentially a kind of iteration on RNNs that get rid of the vanishing gradient problem through a clever trickery that I'm going to talk to you about. So LSTMs, or LSTM neurons, which you can kind of see here, behave a little bit differently in the sense that they're actually made up of 4 neural network neurons inside of the, well, let's call them modules rather than neurons themselves, the LSTM modules.
So I guess what we're saying is that what was a neuron in a traditional neural network now comprises of 4
Exactly, yeah.
inside one.
4 functions inside one, yeah, exactly. So traditionally it was just one activation function. You got the inputs. The input was then taken through the activation function, and if it was activated, an output was spat out. Now we have these 4 activation functions, essentially 4 neurons in there, as well as some what looks like confusing arrows, strange pathways, but they essentially act as gates. And the main idea behind an LSTM module is this little long line across the top, which is the module state. Now, the module state allows the LSTM modules to keep a long-term memory, well, both a long and a short-term memory, as the name suggests, of the whole network. And what these gates essentially do, I'm not going to go into the complexities of them, but essentially what these gates do is they take the input, xt, and they decide how much of that input should be used to update the module state, if any at all. So for example, this first gate here, you can see that there's 3 sigmoid gates and 1 TANH gate there. The sigmoid ones essentially say how much of that input should be used to update the module state. If it's 0, it doesn't update anything. If it's 1, it updates the whole module state and anything in between. And the implementations do differ. That's the one thing I have to say. LSTMs, although the core idea behind an LSTM module is roughly the same, they all roughly have, in fact, they all have 4 kind of gates. The actual placement of the arrows differs depending on what research paper you read. So you might see very slightly tweaked implementations of these, but in essence, they do the same thing. They update a module state, and it allows the neurons to keep a good long-term memory of what's going on, essentially. Now, the best way to actually, I guess, show you this and show you what you can do with it is to show you an example. So a super simple example here would be to model a sine wave function. A sine wave function is pretty great. It's a recurring pattern. Now, a traditional neural network obviously would struggle because it wouldn't have that history. If it just got shown a window, it wouldn't have that history to be able to map the whole function. But I'm hopefully going to explain how an LSTM goes through that. So what we have here, so we've got a sine wave, and we've got the data points of that sine wave in a CSV file, 5001 time periods. And we are going to split those into its standard kind of data science example, split it into a training set and a testing set, 90 to 10. And our training set is going to be windows of 50. They're going to be progressing windows, so sliding along by one each time. And an example of a window would be something like that. So this is what gets fed into the network state at each time period. The network just sees these kind of snippets of the sine wave. It doesn't see the whole thing. It just sees little zoomed in versions, and from that it has to extrapolate on once it learns the weights. It has to extrapolate on what it thinks the next predictions are given a set of windows. So how you then do that? Quick show of hands as well. Who uses Python here? Quite a few people. Awesome, cool. So the code that I'm going to show you a bit later on is Python code, and although it uses a TensorFlow backend, I use an additional library on top of that called Keras, which is very, very nice. Essentially, it's almost as simple as stacking Lego bricks, but with neural networks and NSTMs, and it makes it really quick and really simple to actually produce these models really quickly. How you actually load this data into an LSTM network, or the network, is you load it into a three-dimensional array. So the dimensions, the first part is the total windows, 4,500 or something, obviously, training windows. The second part is the window size, so 50, and the third part, for this particular case, is just 1, and that's essentially the dimensionality of the data. Obviously, we only have the one-dimensional data here. However, the good thing with LSTMs, as with normal neural networks, is you can have many input dimensions to them. So you can have multi-dimensional time series sequential inputs, which is really gives it a kind of more powerful feel to it. Go for it.
Sorry, quick
Yeah.
one. Is that something that is optimizable, the window size, or is that something we'll have to specify?
Obviously you can optimize the process yourself by trying different window sizes and seeing which ones work the best, etc. I've just used the length of 50 because, just a hand in the air kind of thing. No reason. I don't know if it's the best window size for this. I didn't really have time to try a different optimization method, but as with all hyperparameters, you can see which ones are optimized for the best results for your particular problem. Yeah.
Give us some examples of this multi-dimensional. Did you say multi-dimensional? What was that?
So essentially, as with normal neural networks, you can have rather just one input into the whole network. You have many inputs, essentially a multi-dimensional input. The same can apply to LSTMs. So just because you have a window of length 50, that is actually only treated as an input size of 1, because it's only one dimension. The length is 50, but it's only one dimension because you're only giving one dimension of input, essentially. So, for example, if you had, a stock market, you could specify multiple dimensions along that sequence. So you have a time sequence of price returns, volatility, volume. There's 3 dimensions that you could all bunch up at each specific time period, and you could add that into the network as well, to hopefully give you better predictions. Yeah.
They're really variables. Like
Sorry?
Say if you would say it was medical data,
Yeah.
sensors, it could be somebody's heart rate, blood pressure.
Yes,
they're
absolutely.
variables.
Exactly. Yeah. So you could use as many variables as you want. Obviously, the more variables you use, especially on a network like this, it's gonna really exponentially increase the time it takes to train the network. So you might have to look at playing with dimensionality reduction. But yes, you could, blood pressure, heart rate, add many variables to it, which, really gives it room for kind of good potential use cases, I feel. So moving on to the actual prediction of this particular sine wave. The network I actually used is, you've got one input of, one dimension of size 50 windows. Then you've got 2 hidden layers. Again, as per a completely normal neural network, you've got just hidden layers, and the LSTM modules are treated essentially as normal neurons now. So I've got 2 hidden layers of size 50 LSTM modules, and a second one of size 100 LSTM modules. And then in the end, that feeds into just one single normal output neural network neuron with a linear activation function. That essentially then predicts what it thinks the output should be, the next part of that sequence should be. So in this case, what the next part of the sine wave data should be. And if we take a look down here, so this is actually the model that I've run. The blue is the true data, the green is the prediction, and this is just after one run through, one epoch, one training run of the whole model, and you can see it does actually pretty good. There's a little bit of a shift in frequency here, where it hasn't quite learnt the frequency of the sine function, but other than that, I mean, the scale is almost there. You can't really see it, but it's a little bit off on the scale, but essentially it's learnt the sine wave very well. It's learnt the sine wave pattern really well, which is pretty good. And the way I've actually predicted this, rather than predicting on a step-by-step basis, where you initialize it and then you take a fresh set of testing data and just keep predicting the next step, I've actually only initialized the testing window with the first 50 real-world testing data sets, and then it's predicted the next one, and then the prediction has been appended to the end of that window. It's pushed the window along, and then it's predicted the next one and the next one and the next one. So after 50 time steps, because it's a window of size 50, it's actually predicting on the predictions, and so on and so forth. I'll go on a little bit in the next couple of slides about why you probably don't want to do that for more real-world data sets. But for now, it's predicting the next 500 steps, and you can see it's getting a little bit more and more out of phase as it goes on, but it's done pretty well.
So what you're saying here is the sine wave is what we're trying to predict.
Exactly, yes.
Does it map to the layers above? How does this? Because you have those 2 diagrams like that.
Yeah.
Is it that they are like a neural network, each layer is trying to do something, or is it just a sliding window?
So the sliding window comes into that's the input. So the input is here, and that's fed into the network. So for each window, as it slides along, it gets fed as the input to the network. The network then has its learned weights for the sine function, or for what it thinks is the sine function, and it takes the data from that window. So if we go back a few, it takes, say, this, and it goes, I see this shape. What do I reckon this point here is next? And because it's seen this shape many, many, many times, because it's trained on all of this data up to about here, it knows to a very, very high degree of certainty that, say, for this particular window, the data point is almost certainly here. So that's what it will predict.
So the window size is arbitrary?
Well, yeah, you can specify it to whatever you want. Again,
In your example, you have just a window size of 50 because you decided to get 100 samples.
because I decided to what? Sorry.
To get 100 steps.
Yeah.
Split.
I chose 50 completely just out of thin air, completely arbitrary. I didn't do any kind of optimization processes on. Well, it wouldn't really matter on a sine wave, but again, on more real-world noisy data, you'd probably want to have some sort of optimization process to choose what the correct window size is, and it will also apply to what you're hoping to achieve out of that real-world data. You're hoping to just predict the next time step, or you're hoping to predict the kind of momentum of the real-world data. But actually, funny enough, we'll go on to that now.
Then you decided the number of neurons you have on your first layer, or second layer here, according to your window size.
No, and I did notice that just as I was speaking, that the second layer also has 50. I probably shouldn't have done that just because it might be a bit confusing. It's nothing to do with window size.
Okay.
It's again just an arbitrary number that I chose, 50 and 100. It could have been a 60 and 120. Again, I haven't used an optimization process to get to cross-validate across different networks to see which one works best. But yeah, cool. So I think it's probably best if I show some real-world examples. So seeing as we're in IoT here, I got some data from a household smart meter, which predicted minute-by-minute energy usage of said particular households. And I think I got about a couple of 100,000 data points from that one and trained on that. And essentially I used the exact same model that I used for the sine wave. In fact, I think I used exactly the same one. The only difference I did was I normalized the input a little bit, because now we don't have a nice uniform between -1 and 1. Now we have noisy data that goes up and down by large increments, which neural networks don't particularly like, and the training kind of goes all funky if you don't normalize the data. So with the normalized data, I then just fed it through the same network, and as you can see, actually now you don't have, so the blue data, the blue line is naturally the true data, and the multicolored little ones are the predictions. And now they're not mapping exactly, well, as you'd expect, because the real world data isn't a nice function, it's not mapping to the real world data. What I have done is, you can see that they're all split up, there's many different little lines. I've made a function that predicts the window size, which that one is 80 steps ahead, and then refreshes, updates the next window with the real world data, and then tries to predict the next 80 steps, and then refreshes the real world data again. Because what I found, mentioning back to my earlier point, is if you try and go on predictions of predictions, naturally if there's any kind of error in those predictions, that error is going to grow exponentially, and these predictions will go and converge to something silly. Yes?
That'd be very good on share prices.
Well, yeah, if
We'll get rich.
well, yeah, that's with this graph actually. That the next real world example, this one, that's the S&P 500 index, and you can see the momentum of the predictions, especially for the high volatility parts of the graph, seems to indicate quite well that it's going, that it's going to go up, and it has gone up, that it's going to go down, and it does go down. And I must admit, when I first saw this, I did start looking at yachts and private jets. Unfortunately, I then ran a few more tests and realised that this is, I wouldn't say a fluky window, but they're not quite as nice and consistent as this particular window that I happened to first test on. So, especially say here, you can see in the low volatility areas, it's not quite as accurate. It says it's going up, it goes all around the place. But then that's an example with stock prices I wouldn't expect, especially working in finance, especially with something like the S&P 500, a very efficient index. It's not something that I expect you could predict by just the price history. There's so much more going on in a stock market index that affects the price. But it's fun to look at, and it's fun to have a look and warn of the curse of A, overfitting, and B, getting fluky with your testing windows. So what I would always say and advise is obviously look at other ways to validate the network itself. But for certainly something that does have underlying patterns such as energy usage or sensor data in IoT, where the sensor goes through seasonal changes, etc., that's something that could benefit from an LSTM being able to predict those patterns and being able to distinguish those.
Which is exactly why we are so interested with IoT and LSTMs. I mean, there's that aspect as well, because they do have patterns and they do have repeating patterns under seasonal conditions, but also they have missing things as well. So there are patterns. For example, there is lots of IoT data which is noisy, missing, sensors are, I mean, even the classic smart metering stuff, nobody expects it to be as consistent as anything else. You know, just if it misses values, it's fine.
Yeah.
Sort of thing. And that's why something like this technique is extremely useful for IoT database. And also, one of the use cases which I'm going to talk about afterwards, not fully, is when you don't have a lot of data. That's also the other reason why, because this whole sliding window thing allows you to get more granularity out of limited data sets.
Yeah, no, absolutely. And I'm going to be actually really interested when we go and do some networking later on to just hear what your kind of use cases, or I'm sure all of you kind of have different ideas of your areas of speciality and your areas of expertise and how it could be applied over that. So again, me being a rookie to IoT and not knowing much about the field, it's very interesting to hear all the different areas where this could be applied. So it's very good.
If you say that's 1 day of energy usage and you assume that day 2, day 3, day 4 has similar patterns, are you saying that on day 2, 3, 4 the predictions would become better because it already knows
would be similar?
pattern?
Yeah, exactly.
If
So
it detects patterns which are similar, and
Yes.
therefore it trains itself to those patterns.
exactly that. So and that's the whole point. If the patterns are similar, so if the daily usage or the monthly usage is similar, it's quite hard to distinguish that usage with the naked eye. A, because there's so many data points, and B, because there's so much noise. But if there really is an underlying pattern to it, hopefully the LSTM should, on the right hyperparameter settings, find that pattern. And so on to the next slide. As I said, it is an ever-growing field, and there are LSTMs and RNNs aren't the only sequential neural networks. There's new stuff coming out, generative models, DeepMinds, differentiable neural computers, and something called progressive neural networks, which I haven't really looked that much into, but from what I have heard about them, they seem very promising. Again, everyone who kind of uses these right now, the big players, Google, etc., they're kind of keeping their cards close to their chest of how they're using them and quite how they work. So it's quite hard and a little bit overwhelming at times to just get all the literature on this. The way, obviously, the big players, Google, etc., use these is not just kind of on their own, but as part of a kind of very deep architecture. So they have lots of different networks, parts of it being LSTMs, parts of it being generative models, parts of it being normal vanilla neural networks for their particular application, whatever it may be, self-driving cars, etc. And these deep architectures then, obviously, when you have the hardware to train them, become immensely powerful. And I'm sure you've all heard crazy and awesome stories of how Google, etc., have been able to use these deep architectures to do crazy new things. But yeah, so that's a quick overview of just LSTMs.
Sorry, before I
No.
like this statement because
Yeah.
it's so true. Currently, the
yeah.
unpopular brother of the neural network for the sexy image recognition, etc. Because that is so true.
Yeah.
Because at the moment, a lot of deep learning attention is going to image recognition. Whereas this is a little bit its unpopular cousin or step cousin, but for us, it's extremely important because of IoT data sets, because of any form of prediction with a time series, because almost stock markets and all that kind of stuff, everything comes under that. In fact, Joshua Bengio, who is one of the 3 guys who is connected with the deep learning stuff, and he's connected with me on LinkedIn, and I asked him this question about a year ago, and his book is excellent if you are trying to buy it. I'm already pre-registered for it already at MIT Press book, and he said the same thing as well, that this is like it is not a problem, it's just that it is not a focus. It's just something, but for us, I think this is far more important than anything else. I'm glad you.
Yeah, no, absolutely, and I mean, it makes sense if you look at people like to see the outputs and see real world examples of the things that they do or the things that these things are capable of, and what's the best way to see outputs, and that's pictures, videos, labeling pictures, video analysis, and that's what convolutional neural networks are, and that's why they're so vastly popular. If you type in deep learning into Google, I'm sure the first 10 results will be convolutional neural networks, and you'll see very little about LSTMs because it's just quite hard to visualize apart from on a time series graph the effects of LSTM neural networks. On the other hand, the other thing that LSTMs are obviously used for in a sequential manner, stuff like self-driving cars, is far too complex to get into. So convolutional networks kind of offer that halfway house between being simple enough to understand and not being a crazy deep architecture, and something that people like you and me can implement without being Google, and can also see the results of. Whilst, you know, the LSTMs, they're not, unless you're very interested in a specific field like IoT or financial time series data, it's not going to be as interesting and as applicable to you. So, yeah, it's a good point. It's a good point.
So I have one observation, if I understood everything correctly. I can see a parallel between these long, short-term neural networks and the low-pass digital filters. Because, for example, obviously we are removing the noise from the input, something what digital filter actually does. I can see this, like in electronics we have digital filters for digital signals, and here we can use this basically to remove the noise from any kind of signal, real world signal, or data, which would be anything basically. So it's a kind of filter, provided that obviously there are patterns. And actually in every signal can, every data sequence, no matter how it looks, it can be actually divided into that Fourier series, I can't remember now, but basically some periodical signals, or periodical data. That's my observation.
It's a fair point, and it does in some aspects. It obviously does work as a filter, removing the noise and getting hopefully any kind of discernible patterns in there. One obvious place where I'm sure this probably surpasses the filters is the fact that this can do it on a multi-dimensional field. As said earlier, if you've got, you might not have a pattern just on a patient's heart rate or just on a patient's blood pressure, but actually combine heart rate, blood pressure, and a couple of other variables together over that time series, and there might be some sort of hidden multi-dimensional pattern in there that you physically couldn't visualize, but that the neural network can kind of tease out.
So such a time series which has got multiple dimensions, like the heart rate and stuff, how would it look like? Would it be a combined wave for that, or would it be 3 separate things?
It would be 3 separate. If you're stripping out the individual factors, individual variables, essentially, it would be 3 separate things on the same time scale, so it has to have the same time series naturally, but three very separate
Three
variables on that.
separate things, and they would be feeding into the LSTM
Exactly.
at the
Yeah.
same time, and therefore
Yeah.
you will see three distinct inputs.
Exactly. Yeah. So using the patient example again, if you've got blood pressure, heart rate, two variables over, starting from T0 to T50 at 1 minute samples, you would have to have those samples, the same between the blood pressure and the heart rate. But yeah, then you could feed those uniformly into the network.
So basically, I think if multi-dimension they trained separately and then just at the end they will combine them together, combine the result together.
No, I think they're not trained separately. They're trained as a whole of the network. The best way to look at this is, again, if you just look at a normal non-LSTM, normal vanilla neural network. The multi-dimensions are like the many different inputs. The many different inputs aren't trained separately as an individual input. They're fed into the network as a whole, as the n dimensions that form the network, and it's trained upon that. It's the same in LSTM neural networks. Each from the window, each time step of that window is fed into the network and trained on that. And if that time step has 1 dimension or 5 dimensions or n dimensions, it's trained on the dimensions as a whole. Awesome. All right. As I said, I'm now going to quickly go through, for those of you who are interested, do a very quick code example in Python. Again, all this code is available on my GitHub, and I'm just going to go through the code that renders this, so you can see actually how simple using Keras is going to be. For the S&P 500 data, I have a single CSV file, S&P 500.csv, and it just contains all the S&P closing prices from, as I said, I think 1st of January 2000 up until somewhere in mid-2016, prices on a single line. I've got 2 files, a run module and an LSTM class file. So the run file essentially just provides the main thread of execution for the whole thing, and the LSTM Python class essentially builds a network and transforms the data. The main execution thread for the run file and where everything gets done is this little snippet down here. So you can see here we define the sequence length, so of 50, that can be anything. The number of training epochs, which is 1 at the moment, but again, you can, hopefully to get it more accurate, you can optimize that to be any kind of training number that you want, and the theory is that the more you train, obviously the more accurate it'll be. Here we then load the training and testing data. So if we go to the actual LSTM class file, and I've defined a load data function here. It takes a file name, it takes a CSV, very simply it just reads all that, it splits it up, it puts it into a long array, and then it transforms it into a NumPy array. So NumPy being the standard kind of vector mathematical library of Python, which that's what feeds into the Keras neural network model, and you're able to easily and quickly manipulate matrices and vectors within Python, within that library. Here I split it into a training and testing data set. Again, I just, for this one I use a 90% training, 10% testing, mainly because I just want a small testing window. I don't want it too noisy or too big, so that I have to zoom in a lot. And what we do here is we reshape those NumPy arrays to be in those 3 dimensions. So the first dimension is the number of training windows. So for example, in the sine wave, you've got the 5,000 data points. You split that into 90%, about 4,500 training windows. The second dimension is the actual sequence size or window size, which I've defined at, was it 50? And then the third dimension I've just put 1 because it's only single dimensional data. But again, if we were dealing with more complex data sets, medical, heart rate, blood pressure, etc., you could add those extra dimensions in there as well, which would be really, really good. And the one thing that I mentioned earlier, with the real-world data, you're just going to normalize it, because if you've got real-world data of crazy scales, the training is not going to handle that very well. So ideally you want to kind of squash it down and normalize it to nice values, maybe between -1 and 1, 0 and 1, etc. And as for the windows themselves, I've just normalized them from treated each window separately. So this is the key point. Each window is treated separately. It's the LSTM networks actually remember in the past, like all the windows in the past and all the patterns in the past, but the window itself is treated not sequentially to the windows that came directly before it. So you'll see down, I can't even, up here, I should probably zoom in a little bit. Up here, I shuffle the actual training set, or the training windows, so they're not in sequence. Within the window itself, the sequence is there, but the windows themselves are not in sequence. That's why the window size actually does matter, and that's why you've got to do experiments and see what kind of window size really works for you, and optimize that to your liking. Then on down here, this is the kind of the meat of the actual of the code, and where Keras comes in, and this is how simple it is to build the LSTM network. That's all it is. 20 lines or so of code. You build the model, you add an LSTM layer. You don't even have to add an input layer, because you just specify the input size and input dimensions. Add the 2 LSTM layers. I think, as I said, the top one is 50 LSTM modules, and the second one is 100 LSTM modules. And then you have this little dense layer here, which is just a single normal neuron from a neural network, completely interconnected to the LSTMs, and that's what then produces your prediction of, well, in this case, what it thinks the next price is going to be for the S&P 500. And with that, I've pretty much gone through the whole model. These, the predict, point by point, predict sequence, etc., these functions are literally just to take the data and predict it. So actually we'll only be using predict sequences multiple, because that's what's applicable to the graph that I'm going to output. The 2 functions prior to that, because I use this framework of code to do the sine wave as well. But essentially we could delete these 2 functions and have well under 100 lines of code to do the whole model. And if we then run the model, you'll see, yeah, it's using TensorFlow, and you'll see how quickly, so it compiles in 0.2 of a second, and then give it a few more seconds, and now it's training on the 1 epoch on 3,500 samples. And you can see how quickly it kind of progresses along. Again, 3,500 samples, it's not that much, but even so, it's progressing on a, not a powerful machine, it's a small laptop netbook, and it trains reasonably fast. Awesome.
Thank you very
Thanks,
much.
guys.
Thank you very much.
Ini kita mau coba nggak nih untuk code-nya? Yang tadi ada sine wave ya, sinus wave. Oke, kita coba ya. Oke, sebentar. Oke. Bermasalah karena di Oke, ini ya wave yang tadi scene wave. Ini sempat ada juga tadi di video yang awal. Waktu dia jelasin tentang yang scene wave. Nah, yang ini ya scene wave. Kita prepare dataset, feature train, feature test, label test, itu load data, datasetnya yang tadi, dataset. Terus tadi di sini juga ya, ini split gitu kan, dari split, terus habis itu dia lanjut untuk bikin create LSTM modelnya. Nah, ini untuk LSTM modelnya, model sekuensial, LSTM, return sekuensinya true, input shape-nya feature train dot shape, terus loss-nya MSE, optimizer-nya ada, di sini activation-nya linear. Pre-model compile, terus model sekuensial, oke. Di kita train modelnya. Oke, kita running epoch-nya. Step per epoch-nya 9. Oke. Ada yang tanya ya, return sequence itu kenapa true dan false gitu ya. Itu berarti untuk waktu bikin model yang ini ya, LSTM 50 return sequence true, yang ini false gitu kan. Nah ini kan layer pertama, layer kedua gitu. Nah kalau untuk kenapa dia true itu karena dia mau akses output dari yang hidden status gitu. Jadi kalau dia mau mengakses itu dia true. Kalau mau akses outputnya, kalau enggak dia false gitu. Kalau nyetel itu atributnya nanti jadi true itu karena itu sih statusnya. Kalau kita nggak akses output statusnya, itu kita tulis false. Yang ini. True berarti dia mau akses outputnya yang status outputnya. Oke, ini loss-nya kecil ya. Prediction, predict, sequence, full model, feature test, enroll window. Window yang tadi di atas sempat dimasukin enroll window. Ya, enroll window-nya 100. Bisa kok, bisa dibikin terus semua. Coba nanti kita coba ya, bedanya apa kalau kita bikin terus semua sama enggak. Nah ini true datanya yang biru, prediction-nya yang oranye. Kita coba ya. Ini oke, kita coba. Ya, cuman output layer aja. Kalau ini kenapa nggak di setiap layer gitu ya ada fungsi aktivasi ya? Nah kan yang ini cuma yang terakhir gitu ya, ini layer terakhir itu ada fungsi aktivasinya gitu kan. Kalau kadang ada yang fungsi aktivasinya 2, entah yang atas dulu ada prelude terus yang bawah softmax gitu ya. Kalau setahu aku tuh emang nggak semua layer tuh harus ada fungsi aktivasinya, karena kan fungsi aktivasi itu kan buat aktifin neuronnya gitu kan. Terus nggak semua harus ada sih, kayak emang hampir semua rata-rata nggak ada juga sih yang semua layer dikasih gitu. Karena satu model yang terakhir itu pasti biasa ada activation-nya gitu. Sama yang paling umum kalau CNN sih banyak sih activation layer-nya gitu. Tapi kalau untuk LSTM kayaknya cuma di akhir doang sih setahu. Atau ada yang model project lainnya, tapi sejauh ini yang aku tahu sih cuma di akhir doang sih fungsi aktivasi. Karena kan ini masuk di satu summary model gitu kan. Yang lama terus activation layer-nya tuh pasti di akhir sih. Nah, ini belum di-share ya link Google Colab-nya. Ya, ini belum aku share ya Google Colab-nya. Nah, ini kalau dua-duanya di true ya. Karena kan tadi dia mau akses ini ya yang tadi aku bilang sih. Ini kalau di true berarti dia mau akses nilainya yang tadi. Terus kalau kita true semua, nih loss-nya beda gitu karena dia jadinya akses dari 2 layer. Dia akses dari layer yang pertama sama dia akses nilai dari layer yang kedua gitu. Kita lihat ya hasil tabel, hasil plotnya. Nah, nih kalau dari dua-duanya kayak gini nih prediction-nya jadian. Ini false karena yang diambil sama nilai dari yang pertama, yang sequence pertama karena ada input shape-nya juga gitu. Kalau yang kedua kan nggak ada input shape-nya. Kita lihat yang IBM stock dulu, kita kopas dulu ini. Copy paste. Masih loading. Kalau tadi ini ya yang tanya data, seharusnya dinormalisasi dulu nggak nih? Not that the stock data will be normalized between 0 dan 1 nih. pakai ini ya. Sini ada penjelasan resultnya. Jadi juga dijelasin ya, remember the model predict 500 step in the future. Nah, ini kita pakai yang ABN stock prediction. Nah, ini oke, ini datanya. Open, high, low, close, volume, name. Oke, ini ada detiknya juga. Di sini kita prepare dataset. Ada note kalau stock price data akan dinormalize antara 0 dan 1. Oke. Nah, nanti yang test setnya itu ambil yang 10% ya terakhir. Jadi ini 10% itu jadi test setnya, yang biru itu training setnya. Oke, ini modelnya kayak biasa. Ini return sequence-nya true, input shape-nya pakai yang feature train ini. Shape-nya 1, dropout 0,2, jadi yang dipakai 80%. Epoch-nya 5, di sini kita training. Kalau untuk prediksi masa depan, apa tinggal masukin tanggal doang atau gimana ya? Kalau ini kan mau buat prediksi, ya prediksi jadi ini data 2006 sampai 2017 gitu kan. Terus adanya cuma date-nya aja kan ini. Kalau untuk time series emang biasanya ini tanggal sih buat yang prediksi masa depan gitu, sama kelihatan juga dari kalau di sini dia ambilnya close ya. Dari yang close terus ya prediksi yang masa depannya gimana berdasarkan itu sama tanggalnya gitu kan. Ini sama ya, pakai enroll window yang tadi 100 prediction label. Oh, ini yang atas. Bentar, kita run yang bawah. Nah, ini yang bawah ya. Jadi prediction-nya kayak gini. Terus true datanya yang biru. Nah, ini label test, predicted stock price. Model predict future test. Jadi future test tuh yang ini. Yang 10% tadi. Terus predict, ini label testnya. Label testnya. Oke. Kayak gini hasilnya. Ini prediction-nya kayak rendah, tapi ternyata true datanya tinggi nih yang biru. Ya, tadi udah 0 dan 1. Di antara 0 dan 1. Udah dinormalisasi. Ya, nanti aku share termasuk aku share semua dataset yang ini ya. Jadi bisa dicoba-coba sendiri. Ada yang Google, ada yang Amazon. Terus juga tadi banyak sih ini. Bisa dicek berdasarkan kode yang depan ini. Ada Amazon ini. Kayaknya ABA ini Alibaba sih. Alibaba, Amazon, Cisco, Google, IBM. Ya, aku share datasetnya juga semua. Jadi bisa dicoba-coba. Kalau yang ini kan baru IBM aja gitu ya. Oke, terus tadi di video itu ada yang household. Nah ini, predicting household. Saya coba yang household. Sklearn, cross validation. Oke, mungkin ada yang berubah penamaannya. Kalau di collab kadang gitu sih, kalau lagi kadang beberapa itu bisa berubah gitu. Kayak kemarin udah nggak bisa pakai yang TensorFlow yang apa gitu ya. Apa itu harus diubah. Jadi kayak ada pembaruan gitu. Oke, dia mau K-fold. Model underscore selection udah ada sih. Itu buat yang trend test. Pakai yang ini ya, berarti. Hmm. Oke. Oke, ini datanya ya. Ada global active power, global reactive power, voltage, global intensity, submetering 1, submetering 2, submetering 3. Tipe datanya float semua. Oke, shape-nya ini ada 7 kolom. Ini datanya sebanyak ini garisnya. Describe ini buat nge-count datanya, rata-ratanya, standar deviasi, min 25%-nya, 50%-nya, 75%-nya, max. Gitu. Ini kolomnya ada 7. Ini buat cari semua kolom ya. Ini 0 sampai 6, berarti kan ada 7 kolom gitu. Oke, ini semuanya nggak ada yang kosong gitu ya, semuanya. Semuanya not. Sini resample over day dan show the sum and mean of global active power. Oke, ini yang resample sum, ini yang mean. Ya, ditulis di sini dia punya struktur yang mirip gitu ya. Yang biru itu yang hasil dari yang global active power resample over day for sum, yang bawah yang for mean. Ini yang global intensity, mean, standar deviasi. Hampir-hampir mirip, tapi ada bedanya dikit gitu ya gambarnya. Terus di sini global reactive power, mean, standar deviasi. Ini sum of global active power resample over month. Kalau tadi over day, yang ini over month. Overman, average, overman. Ini average tiap bulannya gitu ya. Nah yang ini mean of global active power sample of per quarter. Sana ada 4 quarter. Ini mean of voltage over month. Ini voltage per quarter. Oke, yang ini submetering 1 per quarter. Oke, kalau buat yang notebook yang ini nih cuman untuk time series data analisis gitu ya. Jadi nggak terlalu yang machine learning-nya gitu. Ini buat cara lihat analisis datasetnya kalau datasetnya besar banget gitu ya. Jadi kan dataset ini besar gitu. Di sini dia nge-compare mean of different feature sampled over day. Hasil compare-nya. Ini yang over week. Ini ada kelihatan global active power, global reactive power, global intensity, submetering. Ini kelihatan pakai histogram. Global active power, global reactive, global intensity, submetering 1. Ini korelasi antara global intensity sama global active power. Kayak join plot. Oke, masih loading. Oke, lumayan lama ya ini loadingnya. Oke, udah sampai yang PLT show runningnya. Ini dia pakai RNN nih, nanti pakai LSTM. Oke, ini hasil plotnya, korelasi antara global intensity sama global active power. Sebenarnya kalau gampang lagi tuh, kalau mau lihat korelasi bisa pakai heat map gitu ya. Itu justru langsung kelihatan dari 7 kolom. Tapi di sini pakai yang join plot. Dari join plot yang atas, ya bisa dilihat kalau global intensity sama global active power itu berkorelasi, tapi voltage global active power itu sedikit berkorelasi gitu ya. Nah, ini important observation for machine learning process. Kalau emang ngerjain project yang datanya banyak, harus dilakuin analisis data dulu kayak gini sih. Oke, ada yang tanya. Kalau taunya berkorelasi atau enggak, nah iya, ini rada susah ya dibaca kalau kayak gini ya. Sebenarnya yang paling gampang dibaca berkorelasi atau enggak itu heat map sih. Jadi kalau heat map itu nanti warnanya kayak gradasi gitu, jadi kalau yang makin gelap itu makin berkorelasi antar tabelnya, antar kolomnya gitu. Kalau yang ini kan kayak dimasukin satu-satu ya, X-nya apa, Y-nya apa. Kalau untuk heat map itu langsung 7 kolom sih. Semua kolom yang ada di dataset itu. Dicek dia berkorelasinya sama mana gitu. Kolom yang mana dengan kolom yang mana. Kalau ini karena ngumpul di sini ya mungkin. Aku belum pernah sih kalau pakai yang solid plot ini. Oke. Global intensity sama active power berkorelasi, iya sih, ini karena ininya sih. karena ngumpul gini nih. Kayaknya karena itu sih. Dia disebut berkorelasi. Nah, kalau yang selanjutnya kan si voltage nih, voltage sama global active power. Nah, yang ini dibilangnya loss correlated. Nah, ini kita coba lihat ya, kalau yang loss correlated itu gambarnya kayak apa habis ini. Tapi kalau ini jadi lama banget sih, karena dia harus per datanya kan ya, titik-titiknya itu. Sedangkan tadi itu datanya banyak banget. Nih, 2 juta baris. Nah, ini yang tadi loss correlated. Oh, ini ada yang di negatif. Ada yang di negatif 0 sama negatif 0,04. Kalau dari datanya emang ada negatif nggak ya? Plus. Coba nanti bisa dieksplor lagi yang kalau ini join plot. Nah, kalau dari yang ini kan jauh lebih kelihatan gitu ya. Tadi ini 0 itu maksudnya kolom pertama, 1 kolom kedua, 2 kolom ketiga gitu. Ini kolom ke-7. Ini kolom ketiga sama kolom pertama. Berarti berkorelasi. Kalau dia sama kolom itu sama dirinya sendiri jelas berkorelasi, jadi dia 1 nih. Nah, ini ada kan yang nomor 3 sama nomor 0 ini berkorelasi. Ini kalau udah di sampel manir. Ini yang buat min-nya ya, korelasi of min of feature sample-nya. Ini machine learning-nya. Series to supervise. Ini resampling data of an hour. Kolomnya 7, barisnya ini. Terus ini kita scale feature-nya range of 0 sama 1. Jadi di sini kita pakai train base dari resample data yang tadi over-hour. Kita pakai yang DF resample, var min max, terus ini reframe, series to supervise pakai yang tadi di atas fungsi series to supervise. Ini drop column yang kita nggak mau predict gitu. Ini head-nya. Nah, di atas ini melihatkan 7 input variabel input series dan 1 output variabel global power, global active power. Nih. Oke, di sini split train sama tes pakai yang tadi ya, reframe. Udah pakai yang reframe. Ini yang reframe yang udah ada di drop. Volume yang nggak mau kita predik. Nah, itu kita masukin di reframe. Train time-nya 365 kali 24 setahun kali 24 jam gitu. Terus ini split train, train X, train Y itu jadi train tes X sama tes Y itu tes ini sama ini ya, train tes. Terus reshape inputnya buat 3D sampel, timestamp sama feature. Terus ini di print X-nya, train X shape-nya, train Y shape-nya, terus tes X sama tes Y ini. Di sini model arsitekturnya STM dengan 100 neuron. Terus drop out-nya 20%. Neuron di output layer untuk predicting global active power. Ini input shape-nya akan dalam satu time step dengan 7 fitur. Ini pakai my loss function dan efficient Adam version of stochastic gradient descent SGD. Modelnya akan fit 20 training epoch dengan batch size-nya itu 70. Ini ya lagi training. Oke, nah ini udah keluar ya. Sini model loss-nya, train loss-nya sama test loss-nya. Terus hasil RMS-nya 0,615. Oke, yang merah ini prediction-nya, yang biru itu aktualnya. Jadi di sini dia cuma compare prediction buat 200 jam gitu ya. In range 200 jam nih. Kayak gini ya untuk yang post-hoc. Dimulai karena datanya banyak, mulai dari awal analisis, lihat korelasi, terus habis itu baru masuk ke model machine learning-nya. Oke, ada yang mau tanya mungkin? ini itu ada jam 21.41 gitu ya. Terus masih ada satu yang Tesla. Kalau nanti ini kan aku juga mau jelasin buat sedikit mekanisme demodenya gitu ya. Ini Teslanya mungkin aku share aja ya nanti di grup Google Classroom, di Google Classroom ya. Bukan yang ini. Aku share tentang demonya ya. Tapi sebelum itu kalau mungkin ada yang mau tanya tentang tugasnya dulu boleh juga, atau mau langsung ke demo-nya aja nih. Gimana yang lain? Ini kita mau sisa waktu yang ada mau coba kita bahas mekanisme demo-nya. Oke ya, demo-nya ya. Oke, jadi ini buat mekanisme demo-nya. Nanti kita akan share untuk yang ini juga. Jadi semua dapat akses buat lihat mekanisme ini. Terus di sini pengumpulannya itu proposal, slide presentasi, video durasi 10 menit, menjelaskan model machine learning yang telah dibuat oleh tim, terus code GitHub dan dokumentasi. Nah, untuk besok tanggal 2 itu akan dimulai jam 11. Nggak selesai itu untuk penjelasan datasetnya. Hari ini bakalan kita share sekalian di Google Classroom untuk yang kelompok dan pembagian dataset gitu. Nah, ini untuk timeline-nya ya, 16 Juli itu yang dikumpulin proposalnya, nanti tanggal 27 Juli itu yang dikumpulin video presentasi, GitHub, sama dokumentasi gitu. Tugasnya outlier-nya dihilangkan dulu nggak? Boleh kalau mau dihilangin, karena kan nggak ada yang benar, nggak ada yang salah gitu ya kayaknya. Jadi kalau tugas kan nanti kita koreksi berdasarkan model yang kalian buat gitu. Tapi itu ikut dari kalian mau bikinnya gimana nantinya. Cuman yang kalau dari yang kita kasih, yang kita rumpangin code-nya, yang cuman code here itu kalau udah diisi semua, yang itu juga udah bisa benar semua sih. Gitu. Sama datanan dihilangkan. Boleh sih kalau mau sampai yang dianalisis datanannya dihilangin gitu juga nggak apa-apa. Paling minimal diisi sampai yang code here, yang ada tulisan code here-nya itu diisi semua. Itu udah nggak apa-apa. Gitu. Kelompok dicampur dengan kelas lain. Nggak, ya, nanti kelompoknya dicampur sama kelas lain gitu. Terus nanti ada template proposalnya itu dikumpulin 16 Juli itu 2 minggu lagi gitu. Sekitar 2 minggu lagi, terus dokumentasinya kayak apa, GitHub. Terus isi videonya ini nanti untuk kelompok karena kelompoknya itu kita baginya kayak yang cowok sendiri, yang cewek sendiri gitu. Apa bisa ngajukan pengen kelompok siapa nggak bisa ya. Terus untuk kelompok yang cewek sama cewek, yang cowok sama cowok, karena sekalian untuk campaign-nya yang woman in tech gitu. Jadi yang cewek akan ada yang cewek sendiri gitu. Ini nanti kalau lihat nama kelompoknya itu cowok semua, isinya cowok semua satu tim, kalau yang cewek isinya cewek semua satu tim gitu. Terus ini nanti untuk data setnya kita kasih akses. Tapi kan kemarin udah isi ini ya, Bu. Google Form itu kan ada diisi jenis kelamin gitu kan, laki-laki perempuan. Nah, kita dari itu sih, dari yang ada di Google Form gitu. Jadi aku kasih akses dataset ini. Ya, kemarin ngisi. Di ini nanti aku bagiin buat dicek. Langsung ke drive ini. Penjelasannya juga. Itu. Sama untuk yang grup demo D ini ya. Nanti kita bagiin. Kemarin kita bikin grupnya itu juga pakai ini sih, pakai machine learning. Karena banyak banget kan. Terus ada yang isi double, kita kan nggak mungkin ya cek satu-satu siapa yang isi double, jadi kita masukin di Python. Buat cek satu-satu yang double, kita drop gitu. Jadi nanti kalau ngerasa udah isi terus namanya nggak ada, boleh nanya ya. Karena siapa tahu model yang kita buat itu ada yang error gitu ya. Tapi kayaknya enggak sih, nggak ada. Udah kita cek satu-satu juga. Tuh. Nah, besok ada 20 dataset kan yang akan dijelasin. Jadi nanti kita kasih link untuk lihat datasetnya kayak apa. Jadi bisa mungkin dieksplor datasetnya buat besok ditanyain gitu. Itu untuk apa, guna yang itu untuk apa. Kayak gitu. Karena kalau dari mekanismenya itu segala bentuk pertanyaan demo D hanya akan dijawab pada tanggal 2 Juli gitu. Untuk peraturan yang demo D-nya. Oke, ada yang mau tanya nggak nih? Nanti aku bagiin di Discord juga ya linknya ini. Sama link grupnya. Terus untuk ini, format penamaan pada Discord harus diubah nama lengkap gitu ya, biar mudah anggota kelompoknya nyari. Ini nanti setelah Zoom mungkin udah bisa diubah namanya di satu server itu diubah jadi nama lengkap gitu. Di sini pada bisa buat ubah namanya kan ya? Nah, kayaknya itu enggak yang harus berlangganan sih. Enggak harus upgrade gitu. Ya, nama Discord di Discord yang Pro A itu diubah. Jadi itu bisa masuk ke Discord, terus nanti ada settingan khusus buat merubah khusus di satu itu sih. Ya, bisa diubah khusus buat server itu aja. Jadi di DTS Pro A itu ada settingnya, nanti bisa cari nama kita, itu terus kita klik punya kita kalau lewat HP itu kita bisa edit edit ini profil di khusus satu server itu aja. Yang nggak boleh plagiarisme itu code atau laporannya. Oke. Kalau plagiarisme itu di atas 30% ini ya. Jadi kemarin dikasih tahu kalau mencantumkan link referensi jika ada dengan kesamaan maksimal 30%. Terus kalau dia kesamaannya 31%, dia udah dianggap plagiasi gitu. Tapi kalau untuk misal mungkin pertanyaannya kalau 30% ini tuh untuk keseluruhannya atau untuk code sama untuk yang laporan ya. Umumnya sih biasanya referensi itu untuk yang laporan sih. Cuman bisa besok ditanyakan karena besok ada tim DTS. Hari Sabtu. Ya biasanya untuk laporan sih harusnya. Kalau mau bikin video ini, beberapa yang kemarin itu bikin videonya kayak dari Zoom atau dari Meet gitu, terus di-record gitu. Jadi disediain Zoom background buat kalau mau dipakai pas bikin video gitu. Iya, cewek-cewek aja, cowok-cowok aja gitu. Kemarin udah dibaginya kayak gitu. Agak susah. Ya kadang kalau kelompok cowok-cewek kan lumayan ada yang ngerapiin proposal biasa yang cewek gitu. Nanti ada 2 kelompok yang satu kelompoknya itu 6 orang. Sekelompok sama instruktur aja boleh nggak ya? Nanti instrukturnya bikin kelompok sendiri ya bertiga. Nggak mungkin sih kayaknya. Nanti aku share di Discord sama aku share di Google Classroom gitu ya, biar enak. Siapa tahu ada yang jarang buka Discord gitu. Habis kelas kalian upload, nanti aku share langsung. Ya, saya tanya penapasan. Ya, nanti habis selesai kelas, kalian nunggu hasil recording, nanti aku upload. Oke, nanti aku update ya di classroom. Jadi aku kirim untuk yang mekanisme sama aku kirim buat grupnya ya. Oke, nanti aku tag at everyone. Gitu, nanti ini bisa dilihat, nanti aku share juga yang ini. Jadi misalnya tertarik sebenarnya itu bisa sih kayak juga kepilihnya di pilihan 2, tapi sebenarnya juga tertarik di pilihan 1 gitu ya. Kan ini kita kasih akses satu Excel gini ya, jadi kalian bisa coba download dataset yang lain mungkin buat latihan di luar project yang ini gitu. Di luar tugas ini itu bisa. Nanti kita share-nya kayak gini sih, satu sheet ini. Untuk role-nya bisa dipisah per kelas. Mungkin nanti aku bilang dulu ya sama tim, karena yang untuk itu semua di-handle sama tim DTS gitu. Supaya kalau emang yang dibutuhin tag itu kelas D, jadi bisa langsung tag kelas D aja gitu kan ya. Misalnya kalau emang butuh tag-nya itu semua ya bisa di tag yang everyone gitu. Nanti kelompok yang ini gabung kok. Kalau buat tag-tagan yang di itu, tapi jangan perempuan-perempuan aja. Kalau yang perempuan-perempuan aja itu udah diminta langsung sama tim buat perempuan-perempuan aja gitu. Oke, ada lagi mungkin? Kalau saya aja ngerumpir. Pas presentasi ditampilin juga code di collab-nya. Pas presentasi itu yang harus ada di video presentasi itu yang ini sih. Terus nanti bakalan aku tambahin, karena besok itu kan kita baru ketemu gitu ya, yang full semua kelas. Nah itu nanti aku tambahin juga buat fast question answer di sini yang frequently yang FAQ ya. Nah itu nanti aku tambahin semua di sini supaya gampang. Boleh kalau ada kesulitan boleh nanya langsung, tapi nanyanya nggak di jam kelas gitu. Boleh nanya langsung. Komparasi. Ya, antar model. Kalau misal mau dikomparasi atau nanti hasil penelitiannya kayak apa, tuh. Ini besok boleh ditanyain ya, hari Sabtu langsung. Ini semua file yang kayak mekanisme demo ini sama yang dataset, itu semua boleh ditanyain besok Sabtu juga. Buat langsung dijawab. Oke, sampai di sini ada lagi mungkin. Oke, ada lagi? Oke. Kalau udah aman semua, ini udah jam 22.04. Ya, aku share semua termasuk datasetnya ini juga ya. Mungkin kalau udah aku izin untuk stop share screen. Oke, yang bisa open cam boleh open cam. Oke. Kita mulai dari layar pertama. Oke, layar kedua. Layar ketiga. Oke, mungkin kalau ada yang mau tanya, itu besok bisa ditanyain semua ya buat hari Sabtu. Jadi hari ini boleh dieksplor dulu datasetnya, boleh dibaca-baca dulu mekanismenya juga, sama template proposalnya juga nanti udah dapet gitu ya. Oke, terima kasih semuanya yang udah hadir hari ini. Untuk jadwal hari Rabu minggu depan, nanti aku share hari Minggu ya, jadinya diubah hari Selasa atau Kamis gitu. Oke, baik. Terima kasih semuanya. Kita akhirin kelas hari ini.